first chapter is about the vector analysis. Okay, so in the first section, we are discussing what is vector is and how to represent it, and what is the operations and the character of operations that we can act on a vector. And we are discussing about the vector algebra. And in the vector algebra, we saw about the vector operations, which were the first one was vector addition, and second one was subtraction, and in the third we discuss about the vector multiplication. And in the vector multiplication, there were two species. One was the dot product, and then second one was cross, or sometimes we call it vector products. We can say just vector products. Dot product and cross product. And the difference of these two are, so one is the dot product of the two vectors result in a scalar, and the cross product of two vectors result in a vector after the operations. That's the difference. And we saw how we denote it and how it can be calculated. Okay? And in the section 2, and we saw about how to express the vector in an explicit form in terms of a component decomposition. So we saw the component expression of the vectors can be given if there is a vector like this. And a given vector can have three different components, which can be decomposed into x and y and z. Can be denoted like this way. Y and a z and then z. And here ax, ay, az means magnitude of x directional component of vector A, and ay is a magnitude of y direction component of vector A, and so on, and which is actually similar as we wrote in a component form of a vector, sometimes write this way. Okay? But if you include the component of the vector direction x, y, z in each expression, you better write it in this way. Okay? So once you have a component expression of the vector, and then you can apply all those operations of the vectors, addition, subtractions, and multiplication differently. Okay? So with this expression, we saw how we can add, subtract, and how we can do the multiplication. And multiplication here, I mean dot product and cross product altogether. Okay? We saw all this in the last class in the previous class. Okay. So today what we will discuss more is what is a property of this kind of operation a bit more. Let's see the section 1.3, where we will discuss triple products, which is a case where we will multiply three different vectors at the same time in a different way with the different combination of the products. Okay? And the first case we will see is the scalar triple products, which is a case the resulting property is a scalar. So let's say there is three vectors, A and B and C, and let's say we want to multiply all three together, but in a slightly different way. And the first one is the one which can be a scalar at the end. And to have that, if we multiply last two vectors using cross product, the resulting property of the cross product will be vector. Okay? So that if you multiply vector and vector using dot product, and the resulting outcome will be the scalar value, which does not have a directional component. Okay? And how do we evaluate this, and what is the property of this kind of object is the subject which I will briefly discuss of. One nice property of this kind of product, so you product B cross product C and the multiply A using the dot product is actually equivalent to this kind of product, C cross product A and C dot A cross product B. Okay? And so these are the permutation of A, B, C. So here is A, B, C, and dot cross. And then B is shifted, and then C is shifted. A go into the back will be the second one. And then from here, if you permute the A, B, C, like putting C in the front, and the shifting A in the second, and then put the B in the back, and you have this one. And these three permutation of a vector multiplications is equivalent, and which we can give a proof of these equivalence by using the component expression of the vector operation. So if we use a component expression of the vector components, vector multiplication, okay, here. And let's evaluate the second part first. Then what we will have will be A dot product, and second part will be the cross product, can be given in terms of a determinant of these two vectors together with the component form will be from its definition. We saw like it will be X and the Y and Z in the first law. And then in the second law, you put the component of vector B, Bx, and By, and Bz. And in the last law will be this second vector will be Cx, and Cy, and Cz. Okay? And whose determinant will be the cross product of these two vectors. Okay? Then, if you take a dot product of this object and this quantity, will be this A should have a three component, X, Y, Z. And if you take a dot product of this component, and Ax component will be dot producted with the X hat, and Y component will be added here by having a dot product of y component of A and the y unit vector, and z component will be placed here. So if you perform the dot product between A and this determinant, will effectively gives you a scalar value by putting A, B, C in the first column as AX, AY, and AZ. Okay, and the second column will be BX, and then BY, and BZ, and CX, and then CY, and CZ, like this. Okay. So this is naturally given by its definition, like this. And if we use the property of a determinant of the 3 by 3 matrix, that the determinant does not change as you permute each column in a sequential way. Okay? So that if you shift the B into the first row, and then C into the second row, and if you move the first row in the bottom, then the resulting determinant will be equivalent. Okay, so this is actually same with the shift of the row in a sequential way, that the first column, first row can be given by the B vectors, component of B vectors, By and the Bz, and then Cx, and then Cy, and Cz, and Ax, and Ay, and Az, and whose determinant is equivalent to with the original one. Okay, as like a third one will be also can be same if you shift one more, will be Cx and Cy, Cy, Cz, and Ax, Ay, Az, Bx, By, Bz. Okay. Of course, if you just fix this and then flip these two, then there will be an extra minus sign will come out in your determinant. But the determinant value is invariant under the permutation of the row, as you put the B in this first and the C second, and then back A in the bottom. Okay, so that these three are equal, will be the equal value, such that this already means. So first one, as you saw, was the from its definition A dot B cross product of C, and second one is a B dot C cross product A. So will be B dot C cross product A, and the very last one will be C dot cross product of A, C dot A cross product and B will be C dot A cross product of B. Okay. So that from each definition, we saw these three different way of multiplication, multiplication of three vectors in this different way are actually equivalent. So these are the end of proof. Okay. So this is one way you can think about a multiplication of three different vectors. Okay? And let's see the second case, which is the vector triple product. So vector will be the, if you have three vectors A and B and C, what we will see will be the cross product of this and this. And here, as we discussed in the previous class, the order of performing the cross product is important, such that if you take a first cross product first and take a second cross product, is not the equivalent with the taking first cross product first and the second cross product in the second. So in this case, whenever you take a triple cross product, you also need to specify the order of a cross product. In this case, let's see the case of the second cross product is performed in the first. It's like the order is important. Okay. So the resulting vector. So and second thing you should be careful about this is, since this is a all vector cross product, such that if you take a cross product of B and C, this quantity will be vector. And then after that, you take a cross product of A and the second big vector. Okay? And since the cross product is the vector cross product, such that resulting outcome will be the vector at the end. Okay? So resulting quantity of this should be vector. And if you analyze them using a component expression, the resulting one will be in this shape. B times A dot product of C minus C vector and A dot B. Okay? Now this is a kind of formula you can prove using a component expression of each vectors, such that whether these two are same or not. But what you can see here is that since A dot product C, which is a scalar quantity, is actually multiplied on top of the vector, and which is subtracted by the C vector, which is multiplied by the scalar value A dot product of B. Okay? Such that this is a vector subtracted by a certain vector, which will be at the end will be the vector quantity, which you will see here. But how this become this will be the one you should actually analyze by yourself. And this is a kind of formula you better get to know by having the right sequence of the vector as its results. So we call it this formula as a back-cap rule. Back-cap rule, just for the matter of memorize the formula. Okay? So if you multiply A, B, C in a sequence like taking second product first and the first one will result in the B minus C, and the first part of B is multiplied by the A dot C, and the second part is multiplied by A dot B, like this, and which we call, its rule is a back-cap rule, and you can actually prove by component expression. Okay, which I will skip here because it's a bit lengthy. Okay, but here I will tell you a couple of things you should be careful about it. That this is not same with the case you take A cross product of B first and take a cross product of C. Okay, which we already saw in the previous class. And in this case, if we analyze this, so what are those? So let's say A cross product of B. Let's say if there is this kind of vector operation, then we can analyze this in a slightly different way using the formula that we have. In a way, first of all, we can actually switch these two vectors by putting minus sign in front. C cross product of A cross product of and B, like this. Because this quantity, A cross product of B, in the parentheses is nothing but another vector. So all you have to do is putting minus sign whenever you change the order of the vector for the multiplication of the cross product. And then once you have this kind of shape, you now can multiply back-cap rule that we know. Okay? So we'll be with the minus sign. So back-cap rule is the second vector will go into the front, will be A. So A C dot B, okay, minus cap means the last vector will go into the front, C, and AB. So in this case, will be A will be C, in this case, in order. So, sorry, this must be cap means the C, and then C will be the last vector, so which will be the B in this case. So will be C dot A. Okay, like this. And the resulting vector in this case will be, with the minus sign, will be B times C dot A, which is the same with the first term here. Okay, so permutation of dot product does not change the property, so that the first term will be same, but the second term will be minus A C dot B, like this. Okay, so here if you compare this multiplication together with this multiplication, okay, then the first term will be same, but the second term is not equivalent. So changing of C and A so if you change the parentheses from here to here, then you change the C and A, swap the C and A like this, and then you obtain this vector as its result. Okay, so that's the bit of differences. So once you have this kind of a rule for the vector multiplication, especially in this case the triple cross product, then you can actually calculate the. So once you have this rule of this rule together with the triple product with the mixed dot product and cross product, and then you can actually apply any kind of a multiplication of a vector product, because you can sequentially apply the vector multiplication rule to the vector multiplication more than 3 and 4 and 5 and so on. Okay? So let's see the case like this. This is a typical exam problem or quiz problem. Prove that, let's say, there is 4 vectors, in this case AB, dot product, and C cross product of D. Okay? Let's say you have this one, so then in this case, this is a vectors, so that like a cross product of vectors will be vector, and it's same in the second vectors. And since these two are vector quantity, you can actually make a dot product of these two vectors here. And the result of this is interesting in a way, given so the resulting quantity of this will be the scalar quantity, because you apply the dot product at the end between the two vectors. So that resulting property will be scalar at the end. And the results will be in this shape. So A and C times B dot D minus A dot D and B dot C. Okay? So this is the one of the multiplication rule. But you don't necessarily have to remember this once you know the backcap rule and any other vector multiplication rule. Okay? So let's see how we can prove this one. Okay? You can think about it for a while. That if you remember the previous formula, then this was the scalar triple product. Was that you multiply a vector dot product and the two vectors cross products. Okay? And if you look at the first formula, and if you think first two vector as a one large vector, and then second and third as a different two vectors, then what you can do is you can apply the scalar triple product formula. Okay? So that what you can do in this case will be, let's say, if you have A cross product of B dot and C cross product of D, D, and you can see this first one object as a one big vector, and then if you remember the permutation rule of a vector scalar triple product case was that you can actually pull out the C in the front and then D in the next and A cross product B in the back. In a way, you can put like this way: C and D cross product and the large vector, which is nothing but a vector obtained after the cross product of A and B. Okay? So A cross product of B is nothing but a big chunk of a vector, which is obtained after the vector operation of the cross product of A and B. Okay? So, and then if you apply the multiplication rule, then you will have this one. Okay? And then once you have this formula, then you now have a formula in the big parentheses, brackets. Then you have a triple multiplication using only the vector cross product, which now you can apply the backcap rule that I just showed you. Was that C dot product? And here, if you apply the backcap rule, C dot product, and backcap rule will be B will be the second vector. So in this case, it will be the first vector, and you do the D dot product of B. Here, I better denote the vector notation like this. But it is clear that this is a scalar which is multiplied to a vector A. Okay, and then second part will be the minus. Back cap. Cap will be the C will be the very last vector. In this case, it will be B. So B vector and dot product of these two. So D dot product of A will be the formula. Okay. So this is what you have, and then as we saw in the previous class that this dot product is distributive over either plus or minus addition or subtraction, such that in this case, what you can do is you just multiply C and A using a dot product, and this object is just the scalar, which you just multiply it as is scalar, and then you can actually change each order without changing each property. Will be A dot product of C can be the first one times the cross product, dot product of B, okay, minus. In the second part will be the C dot product of B, and whose order can be changed in a way B dot product of C. And the very last one as well can be the D dot product of A, whose order also can be changed. Okay? And then if you, so here, from here to here, you use the backcamp rule. Okay? And as you saw, from here to here, you use the distributivity Okay? And so you just distribute C to the first term and the second term, and then you obtain this. And this is the same with the second term in the equation. So this is the end of proof. Okay? Okay? Is this clear? Okay. So actually, in this way, once you have a vector product rule, then you can actually apply these to analyze the many different multiplication of many different vectors. Okay. Okay. So. We are now slowly get to used to the vector operation. And now let's define a couple of different vector notation, which is more close to our description of the particles in a space, which we use sometimes using position vectors. Okay, so here. I'll just give you a couple of conventions which will be useful in a description of electric field and magnetic field in a space. For that purpose, so this is just a definition of conventions. Position and displacement and separation okay. So we slowly use the notion that we introduce in a mathematical term in the description of a physical object. Okay. So that definition of a position vector position vector is given. So let's say if there is a vector like this, then we usually write the position vector using the value of the each coordinate in a component x, y, z, and that can be given as x and x directional component, and y and the y directional component, and z and z directional component. Okay, so this is what we usually say position vector, which is the same to say that if there is a particle in a position r, then and if we have a Cartesian coordinate whose component is x, y, z, we usually write it as x, y, z like this. Okay? But sometimes, to have a more precise description, we want to write that position vector not just in a coordinate-wise way, but with the component way like this, you're using the unit vector in a direction of the x and y and z. And we sometimes use it like this. And the direction of that position vector is given by the unit vector representation. So unit vector in the direction, which means what is the direction of a position vector while its magnitude is 1, is given as a unit vector. And let's say in that way, the description is given like this. So unit vector of the that position vector will be given, which written like this, and will be same with the divide the position vector by the magnitude of position vector, such that if you get the magnitude of this will be the 1, while this unit vector will denote the direction of the position vector. Okay? So that since we know the Pythagoras formula, that the magnitude of this vector is given by the x squared and y squared and z squared. Okay? So that the representation of a unit vector by the x, y, z will be given as x on x direction, and y direction, and z direction, which is divided by the magnitude of the position vector, which will be x squared plus y squared plus z squared. Okay? This is something obvious, but let's just check the representation once more. Okay? And then third useful quantity of the quantity representation related with the position vector is infinitesimal vector, infinitesimal displacement vector. Infinite vector, which is for the case that the position is keep changing over the time, then the amount of the changing of a position vector is usually denoted by the infinitesimal displacement vector, and which we will use differential form of a vector, a position vector, and such that each component is changing in an infinitesimal way, which is given as a component of x and y and z, will be given dx in an x direction. So the infinitesimal change of the x position is put into the x direction, plus dy, which is the infinitesimal change of the y directional component, which is put in the y direction, and dz is the infinitesimal change of a position in a z direction, is put together with the z directional unit component. So this is what we call the infinitesimal displacement vector. So and the fourth one, which I will show you each convention, is separation vector, and we sometimes call it as displacement vector, which is the directional vector which denotes how does the position of a particle is changed. Okay? So separation vector is, let's say there was a particle here in a position given by the position vector R1, is changed its position into a different point whose vector is denoted by the R2. Then you can ask a question, what is the vector which will represent the change of the position of the particle, and which we will call as a displacement vector, or sometimes called as a separation vector. So and which will be just link the two lines of the points and give the direction from first one to the second is written as R like this, called the separation vector, and whose definition is given by R2 minus R1. Okay, so this is a vector subtraction. Okay, to give a notion, the direction of the motion, direction of the change of position of that given particle is given like this. Okay, and if you write this in a component form, so since the position vector is usually written as, let's say, x2 and x direction, and y2 and y direction, and z2 and z direction. So this is a second vector, and then first position vector is written x1 and in x direction, and y1 and y direction, and z1 and z direction. Okay, such that this displacement vector will be given in a component form that will be x2 minus of x1 by collecting these two, having directional component as x hat plus y2 minus y1 has a y component, and z2 minus z1 will have a z component like this. Okay? So this is a component description of a displacement vector. Okay? And the unit vector of the displacement vector also can be obtained, which will be the unit vector of this given vector. Okay, so will be in a form of delta R, which is the displacement vector, and which is divided by the whose magnitude of the displacement vector will be given in a way. This divided by the magnitude of this vector can be obtained in a way x2 minus x1 x hat plus y2 minus y1 y hat plus z2 minus z1 z hat, which is divided by the magnitude of the vector, will be this square plus this square plus this square from the Pythagoras theorem will be x2 minus of x1 square plus y2 minus y1 square plus z2 minus z1 square like this. Okay, so this is a unit vector of the displacement vector. Okay, and from the displacement vector, we can also have a infinitesimal vector in a limited case that when R2 is approached to R1, okay, then this displacement vector is become an infinitesimal position vector in a way. So in the limit R2 go into R1, the displacement vector will become infinitesimal vector like this. Okay. So, and whose interpretation is that if the position of a particle is changing in a space like this, as the time t is changing, then the vector which denotes the position of a particle is given like this. Then at a very short time, the particle will change its position, and the tangential part of its trajectory is actually is for the infinitesimal position vector, which will tell us how does the particle is make a motion in a very short period of the time. Okay, so that's the physical meaning of the infinitesimal vector. Okay, so these are the couple of ways we can apply the vector notation to describe a physical object, which we will heavily use as we deploy our theory of electromagnetism soon. Okay. Okay. And from here, let's change our topic of a vector notation, vectors, as we change the as we see the vector transformation. So 1.5 vector transformation. And so in a way we denote in a way we make expression of the component form of a given vector. We just write in a way it should have an x directional component and y directional component and z directional component. But in general, the direction of a coordinate system is not unique in a homogeneous space. Okay, so that if you like to make a component expression of a given vector, then you should specify the coordinate system first. And as you change the coordinate system, your component expression of vector also should be modified. Okay? So here I will briefly tell you what will be the rule of the to convert one vector expression to the other vector expression when you change the coordinate system. Okay? So the vector transformation is a kind of thing we need because a vector can be expressed or represented differently by two different coordinate system. Okay, so that let's say there is a one coordinate here, have a x direction in this direction and y direction in this direction, and let's say you have a one coordinate system. And if you want to express a vector in a space like this, whose angle with the x-axis is given by theta, then you know the x component will be in this direction. So this will be this length will be ax. Okay? And if you project that vector a into the y-axis, then this length will be the ay. Okay? And together with this a and together with the ay, we can express a vector a in a component expression. So it will be ax in the x direction and ay and y direction like this. Okay? But what if the coordinate system what we have is not in this direction but in this system, but in the other system? It will be nice if I can have different color of chalk, which is not here. But okay, let's use the same color of chalk, unless it's not too confusing, right? Let's say there is another axis of x. Let's say this is the x prime direction, and whose orthogonal component is given like this way, and y prime like this. Okay? So let's say the angle between a and x prime axis will be theta bar. Then the component expression of this a vector in a different coordinate system should be different from the component expression of the other coordinate system, because the x-axis now it's the direction is not x but x prime should have this length rather than this length. Okay, which we will let's call it as a x bar. Okay, and the y component in this case to express this vector a should be projection of a vector this y prime coordinate, such that so this length is no longer same with the other length of ay, so which we will call ay bar. Okay. Then same vector, same a vector can be expressed differently now using ax bar in a direction is now the bases are no longer same. So in this case it's a prime basis, which is not the same basis, and the second one will be y bar in a y direction, but not just y direction, but y prime direction. Okay, so here ax and ay and ax bar and ay bar will be the different value because your coordinate system has been transformed. Okay, so in this case, using the theta, you know that the ax is nothing but a magnitude times cosine theta, and ay is magnitude of sine theta, like this. Okay, while for the case of ax bar will be the magnitude of a, and which if since angle is the theta bar to project to the x prime direction will be cosine theta bar, whose value is not same with the theta. Okay, and A y bar, in this case, will be A times sine theta bar. Okay? So as you change your coordinate from the xy and from xy to x prime y prime, its component value must be also changed. Okay? So here we can ask a question. Let's say we know the component of the first vector, component of the vector in the first coordinate system. Then how would we get the coordinate of the component of the prime coordinate system? Is the kind of question we can ask. Question we have here will be how to obtain a x bar and a y bar from a x and a y. We can ask a question like this. And those can be possible. Those are possible. So since we know the theta and theta prime are not same, in a way that, let's say, the theta is, so the difference between the theta and theta prime is given by pi, like this. Let's define the pi is the difference between, so let's say pi is theta minus theta prime. Okay? Then, to have expression of a x bar, which is from the beginning a cosine theta bar in this case, okay, is now can be changed the theta bar in terms of a theta and pi. Okay, so will be cosine what? Will be theta minus pi. Okay, and here, if you use the cosinus trigonometric functional expansion, then you will have like this. Cosine theta times cosine pi minus sine theta times sine pi. Okay? These are the two are same. It's identity. And from here, what you can do is you can plug in the a into the brackets. And what you have a cosine theta and cosine pi minus a sine theta and sine pi. And here you now know the value of a cosine theta is originally defined in terms of ax, and same as for the ay. Okay? So this can be rewrite in a way ax cosine pi minus ay and sine pi like this. Okay? So that no, okay, so this is a minus, this must be plus. Okay? Sorry about that. Thank you for the correction. Okay? See, you're not slipping. Okay, here, and the same thing can be happen for the case of a y bar. Now you have changed cosine into sine, right? Cosine into sine, but the same, but in that case will be the cosine and sine minus sine and cosine, okay? And so which will be a sine cosine pi minus a cosine and sine pi, which will be, in that case, a sine pi will be ay, so will be in the same way. If you deploy same thing, ay will be ay cosine pi minus ax and sine pi, like this. Okay? So using these two identities, and this, we can construct a matrix transformation rule from a bar, x, a, y, and to x, a bar, and a, y bar, in a way that a, x bar, and the a, y bar. So we collect them, and if we write them together, these can be written as cosine pi and sine pi, and minus sine pi and cosine pi, like this. And there will be ax and ay. Okay? So since you know the matrix product rule, so that ax bar will be this times this plus this times this, and ay bar will be this times this plus this times this will be this. So this is nothing but a new representation of writing our two equalities in a simpler way. Okay? So this is a kind of a simplified transformation rule that if we symbolically write this matrix transformation rule such that this a bar vector now can be written together with this transformation matrix. We call this big object as R, and this one as a vector. So this is a vector, and this is matrix. So we write with a bold face like this. Okay? So this is a original coordinate vector, and this is transformed vector. And this is a transformation matrix. So this is a transformation matrix. So, and this gives the transformation rule from one vector to the other. Okay? So transformation of from one vector to the other can be symbolically written, or is usually given by in terms of matrices, 2 by 2 matrices. Okay. In general, so if you think about the transformation, in three-dimensional vectors space, the transformation rule is usually written as a bar x, a bar y, a bar z, because in general we live in a three-dimensional space, and usually a vector is given by three components, and in that case, transformation rule must be given by the matrix whose components are the 3 by 3. So in a way, so let's say R x x, R x y, R x z, or R y x, R y y, R z z, y z, and R z x, and R z y, and R z z will be a x, a y, AZ. And this big matrix is multiplied to this vector will give a transformed vector like this, because they are multiplied in a way like this, and like this, and like this. Okay? So the other way to write this in a simpler way is using indexes. So rather than we write the older component to write this, we can symbolically write all this in a simpler way, like A bar I, where this I can be changed into the value x, y, z, or sometimes you're using a number rather than x, y, z, as I can be 1, 2, 3, by denoting 1 as x, and the 2 y, and 3 z, like that. Okay? In that case, this matrix must have two components, x and column and row, such that should be R must have two indexes, and the multiplying vector should have one index like this, and they should be summed by the same index j equal to 1, 2, 3. Okay? When you denote x as 1 and y as 2 and z by 3. Okay? So the other expression you can make for this transformation rule can be this, because if you take the x here, so you put the r here, I will be the x. Okay? And then you take the sum of x equal to x, and y equal y and y, and z like that. And the first column will be given when you assigned x to I. Okay? And so on. And as you change the I by y, and then you can multiply second row and the first column, and then give the transformation rule. Okay? So this is the other expression of a transformation rule. And here, this R is the object which corresponds to the transformation. And which we call it as a transformation matrix. Okay? Which is a clear concept. So vector transformation is something about the transforming one vector to the other using a given transformation rule, which are well summarized in the transformation matrix. Okay? That's what we can have. And here we can extend the notion of a transformation matrix into a bigger space using the term called the tensor. Okay? So for the case of a transformation matrix in a three-dimensional space, they only have two indexes. Okay? And each indexes can have a value, either x, y, z, or sometimes you write it as 1, 2, or 3. But for the case of object, we call it as a tensor. It has two properties. One is instead of having two indexes, for the case of tensor, it can have more than two indexes. So the tensor is a certain object which can have a arbitrary number of indexes. Okay? And which gives the property of a transformation of the given matrices, all different tensors. Okay? So if you look at, for the case of a vector, it has only one index, right? So once you have a vector, so for the case of vector, so, okay, let's start from the scalar. Scalar is just the quantity which only has a value. Okay, so in that case, it only can be written as just one character, which will be any number to describe a certain physical property. But for the case of vector, it only has one index, which can be denoted by this one. So which means when I equal 1, it means AX. So let's say like this way. So which means, okay, where I can be go 1, 2, 3. And if it goes from 1 to 3, it can be three-dimensional vector. Okay? So, but matrix is a object. In this case, has two indexes. Okay. So if it's a vector, you can have 1 to 3. But if dimension is higher, you can actually have a number bigger than 3. But the fact about the vector is denoted by the one index, which will tell us about the component, the value of the component. Okay. But for the case of the object which gives a transformation rule, that you should have the bigger space than vector. In that case, it doesn't only have a column, but it also has a row, such that it must be written in terms of two indexes, where in the three-dimensional case, I and j also can be written as any integer numbers, or like x, y, z. Okay? But the tensor is a bigger concept than this. Has a certain object, have a index, more index, so can be two direction, and there can be third direction, and the fourth direction, and so on, so that it can have the many other indexes, and the number of indexes is called as a rank. Okay, so the tensor is so vector is a bigger concept than scalar, and the matrix is a bigger concept than vector, and tensor is a bigger concept than matrix, and which usually used for the transformation of the matrix or the bigger tensor. Okay, so that what tensor usually do is also subject to a transformation rule. So let's say there is a tensor, one has two indexes, can be transformed to one to the other, and it can be given from using a transformation rule. Let's say if there is a K and L, then this one tensor can also be transformed into the different tensor using a transformation tensor. In this case, it can be either tensor or matrix. Should have two indexes, and R and J and L should be summed over the I and J like this. It depends on, and then so the index of I and J can goes from 1 to the dimension that this matrix can reach. Okay, so the tensor is a kind of object, can have a higher number of indexes. So this is, if it has a 2, then this is a matrix. But it has a more than 2, then so the matrix is actually the subclass of the tensor, which we will call the rank 2 tensor. And if it has more than indexes, the rank will become higher. Okay? And that object, which we will call now, which is very general in this hierarchy, is called the tensor. And that tensor must subject to a given transformation rule from one to the other, should all the time possible. Okay? So if there is a tensor, then tensor must have some kind of a transformation rule to make one tensor represented by the linear summation of the other tensor. And that's the property of the tensor, which we just defined here. Okay? So I will stop today's class here, and you can ask a question if you have. Any question? Okay, thank you for your attention.